All right. So in the previous lecture, we have seen this constraint optimization, but constraints of a very special form, the integral kind of constraints. But sometimes constraints might be given to in a pointwise fashion. So let's look at a typical example. For instance, suppose you're told right. Suppose this is something that your system has to adhere to while minimizing J given by this. Okay. So you agree that this is some kind of a constraint, but of course not represented in the integral form. Can you identify with this with something that you already know, maybe by making some change of variables or transformations in your head? Yeah, this is actually a system dynamics. If you think of x as time and then y as a function of x being some system's state that's evolving, state vector perhaps, then this is nothing but y dot is equal to f of t comma x y, which is basically a differential equation that governs your trajectories. So it's like a control system. Yeah, of course, without the input here explicitly appearing. So it's like the autonomous part without the input. Of course, if there is no dependency on x, then you can call it like really independent of t, time invariant, and so on and so forth. Nonetheless, this is the kind of things that you will encounter very often once we move into the optimal control part of this course. So far, we are only dealing with the calculus of variations approach, right? So this is something we'll be dealing with on and off, but this is also a constraint. The question is, based on the method or the technique or the approach that we've discussed so far, we only know how to address constraints of the integral kind using Lagrange multipliers. What do we do when we are faced with something like this, right? So I'll not give you a very explicit proof or some rigorous justification behind why what I'm going to suggest will work. We'll reserve that for the optimal control part of the lecture, where you'll see that we'll have a more satisfactory explanation to everything that we do. But I'll just give you the intuitive understanding behind why what we shall be now proposing is expected to work. So you see, this is like some constraint specified at a particular point. If you are at y of x for a given x, then how does it move thereafter? Think of this like the velocity. So how does it move? What's the velocity pointing towards? That's what's given by this kind of a constraint representation. Yeah. So it would perhaps make sense to assign Lagrange multipliers, which up until this point have been held as constant numbers, like lambda 1, lambda 2, depending on the number of constraints you have, till lambda m. We said that there exists lambda 1 star, lambda 2 star, dot 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 till lambda m star, such that when you have this Lagrangian, yeah, plus summation lambda I star times those mi's. In our previous day's formulation, we only considered one constraint that day, so we only had one lambda, but you could accommodate multiple lambdas subject to the number of constraints that you have. So that works. Now the point is that same lambda works for it because it's supposed to be held constant throughout the entire path. Here you don't know about the whole path at one go, you only know about it on an instant to instant basis. So it makes sense then perhaps to consider that you have something given like this, L x y y prime dx j, okay, subject to m x y y prime equal to 0. You see that this definitely fits in with this, right? In such a case, perhaps if you make this as your so-called modified Lagrangian, right? If you define it like this and then use the same approach that we did the other day, it makes sense at least intuitively, because now, because this is not an integral constraint, you allow this lambda to vary from point to point, right? As you keep evolving over the trajectory, over the curve, over the function, you allow the lambda to also vary depending on the x, because once you have specified the x, the y gets specified according to the curve that it follows. So does the lambda in this case. So this is what we shall now use as our modified Lagrangian, the L hat, and use the Euler-Lagrange equation on this. Okay, that's going to be the approach. Now, in some very special cases, things become a lot simpler. So we shall call them holonomic constraints. What are holonomic constraints? Does anyone know? It's some special kind of property invoked on this. Firstly, either this y prime can be separated like this so that you can integrate this completely and find out what the y is, so that the entire constraint can be represented in terms of x and y alone and doesn't require y prime, or the way it's given to you, it's like this m is no longer a function of, so let's keep this clear, the y is a function of x, of course. So this is the kind of constraint. So the y prime does not appear in your constraint equation. Either it does not appear at all, or even if it appears, it can be eliminated through some process of integration. Okay, those are the kind of constraints that we shall call as holonomic constraints. What's so special about this? If you think about it, it essentially says that this is like some sort of a static manifold, isn't it? It's like the equation of some sort of a curve or some kind of manifold. Now, your entire optimization is not going to be contingent upon searching for arbitrary places, but exactly on that manifold. So it's curves that cannot lie arbitrarily anywhere, but curves that actually meet or meet this criteria, that they lie on this manifold. Okay. So in other words, if you think about it for a bit, it is quite likely that you may not even need to write this lambda separately here if you have already accounted for the properties that are satisfied on this manifold. Is that clear? What I am trying to say here is, suppose you know that the moment you live on this manifold, there is a relation between y and x already given here by this constraint, by this holonomic constraint. It's easy to see that, at least, or let's hope it is. In such a case, if you can relate the x and the y and subsequently the y prime like this, and then you can try and minimize it, perhaps life is going to be a lot simpler, because this does not have to be added with the Lagrange multiplier. You already get the dependency from the constraint invoked in this. Let's give an example so that things are clear, and an example that all of you are familiar with. It's the age-old inverted pendulum example. So we have a massless rod here of length L and a mass of M hanging at its end. Okay, and let's say this is an altered position where you wish to write down the equation. Now you of course know how to write this equation. You can draw free body diagrams and things like that, but the point is, the constraint here is what? If you think about this as the origin, and let's say the position here is qx, qy, the constraint is going to be given by qx squared plus qy squared minus L squared is equal to 0. So the position of y is taken by the two tuple qx, qy. Yeah, it's a two tuple now instead of it's a vector. It's in 2D. Now, if you want to write this down in terms of the qx and qy, you'll immediately see what happens to this. Of course, what's being minimized here? It's a mechanical system. So we already seen that in that case, it's the action it's the principle of least action at work. So it's the total kinetic energy minus the total potential energy. That's going to be the Lagrangian. So what's the total kinetic energy of this object here? Let's consider this as our datum. So the energy at this level is 0. Yes. So what's the total kinetic energy at this point? Well, of course, that's half m qx dot squared plus qy dot squared. Okay. And minus the potential energy. What's the potential energy at this point? Well, if it's 0 over here, this is the height, isn't it? So it's L minus qy, isn't it? Yeah, so L minus qy. So that's the other thing, you see, an interesting observation here. I would like to, okay, maybe we should multiply with the g, of course we should, yeah. The interesting thing here is the addition of this mgl here absolutely makes no difference insofar as your Euler-Lagrange equation goes, because the Euler-Lagrange equation, you see, involves taking partial with respect to qx and qy and qx dot and qy dot and then take the ddt. In either case, that constant term would vanish from either side. So if you take any Lagrangian, the Lagrangian is not unique for a given Euler-Lagrange equation. You can always keep shifting the Lagrangian by some constant terms and you'll still end up with the same equation. Okay, that's just a physical perspective. That's why it's independent of the reference frame in some sense. Okay, so this is the thing, but you have to also be mindful of the constraint. Yes. So what I'm going to write here is plus, now in case here the x is replaced by the t, isn't it? The independent variable x is now the t. So it's lambda t times, this is my constraint. Yeah. So I'll just write qx squared plus qy squared minus L squared. Okay. Yes. So this is my L hat, in fact, right? This part in blue will correspond to the L, the action. The additional part comes in because of the constraint, right? Now, if we are to write the Euler-Lagrange equation for this, it will be in the vector form, right? Because there's qx and qy, it's not a single variable anymore. So it will be in the vectored form. Yes. So what should we write? This L hat partial with respect to, what is it? Qx is equal to ddt of L hat with respect to qx dot and L hat qy is equal to ddt of L hat qy dot. So those are my two equations for this pendulum. I have chosen Cartesian coordinates here. What's this? With respect to qx, if I take, just this term appears, isn't it? There's no other qx anywhere, correct? Because this is qx dot Qx doesn't appear in the potential energy. Qx only appears in the constraint. So it's 2 lambda Qx. And that one is equal to this. What is this? Qx dot appears where? Here. So partial of this entire thing with respect to Qx dot is just mQx dot, another derivative because mass is a constant, and it gives you mQx double dot. Is equal to 2 lambda. Of course, you know that lambda depends on time. Let's make it explicit. 2 lambda t Qx, right? What about the second equation? Again, when we take the partial with respect to Qy, now there is an additional term here. This minus and minus will make it plus. So it's mg plus mg, and the rest of the term is the same. It's 2 lambda Qy. So it's 2 lambda t Qy plus mg. On the left hand side, it's the same as here in case of Qx. This is the only place where Qy dot appears. So it's going to be mQy double dot. And this is my governing equations, but as you will immediately notice, this is not very satisfactory, is it? Who's going to tell me what lambda is? I don't know, I don't have a clue, right? So although in principle you have obtained the equation of motion of this pendulum using in your Cartesian coordinates using the constraint optimization formulation, it seems like, well, I'm not in a position to be able to solve this because of the fact that this pesky lambda is sitting over here, and unless I am able to eliminate this lambda, I'm in trouble. So this is what the standard method we have suggested just now. This is how it presents itself. Let's take an alternate approach. Okay, let's move from the Cartesian to the polar coordinates, and immediately we'll see that now you don't have two variables to account for, because after all the L is fixed. So the only thing that actually changes, even though this one seems to suggest that, oh, Qx, Qy are varying, but they're not arbitrarily varying. There's a particular constraint that they must satisfy while varying, right? But if you sort of make the transition in terms of theta, then theta is the only thing that's really varying in this entire motion, because the pendulum cannot, it's an inflexible massless rod with which this bob is attached. So this pendulum length doesn't alter, the only thing that changes is the theta. So let's try and come up with the same Lagrangian now as t theta and theta dot. You see, the moment you say that the L is fixed, what have you done essentially? You've already accounted for this constraint. So you don't have to augment this with any Lagrange multiplier anymore. Do you see that? Here you had an extra state, that Qx and Qy, there were two states, whereas independently only one quantity was varying. But here there's only one quantity that's varying and you are capturing it through a singleton here. This is not a two-tuple vector, this is a singleton. So this is kind of redundancy free. The constraint has already been accounted for within this setup. So let's write down what the total kinetic energy minus the total potential energy in terms of this theta can be. What is it? Well, you know, because it is attached like this, the only way that this guy moves is in an orthogonal direction to this, that's the velocity. So what's the velocity along this? Well, I omega squared is the total kinetic energy, and this is, since a concentrated mass over here, so it's just ml squared. Summation mi squared is the moment of inertia, which is ml squared. That's the rotational, moment of inertia. So ml squared, and what comes with it? Theta dot is omega, isn't it? So ml squared, theta dot squared. So half ml squared theta dot squared is the total kinetic energy. Half m L squared theta dot squared. What's the potential energy? Well, now that qx qy doesn't make sense, but what does make sense instead is, what is this length? If this is L, then this is L cos theta. So this difference is L minus L cos theta. Yes. So mg into L minus L cos theta. Yeah. Okay. You don't need to account for the L is already accounting for the constraint. So therefore no Lagrange multiplier. That's exactly what I meant when I said that if you have holonomic constraints, this is a huge advantage. Okay. Now then, let's apply the Euler-Lagrange equation on this. So L theta is going to be equal to d dt of L theta dot, which leads us to what? This is plus mgl cos theta. Of course, the mgl term is irrelevant, it's again a constant. So mgl cos theta, the differentiation will be minus mgl sin theta. So you have minus mgl sin theta is equal to L theta dot, that is the 2 comes up here, 2 and half cancel each other out, so ml squared theta dot, but then you have to take a ddt. ml squared is a constant, so it's ml squared theta double dot, ml squared theta double dot, and just like that the m and m cancel, the L gets taken out once. So what do you have? Theta double dot is equal to G by L sin theta with a minus sign, and that is exactly the equation of a pendulum, the accurate one, not the linearized one where you approximate theta to be small and therefore sin theta is almost equal to theta and linearize it. This is the exact equation. So the solution to this would give rise to elliptic integrals in reality, whereas the linearized version gives you SHM, simple harmonic motion. The question is there any connection between this and this, or are we at least going to be able to recover somehow? The trick is you need a lot more work here. The point of this exercise is to convince you that if somehow you can incorporate the constraint, because of the constraint being holonomic, if you can somehow incorporate the constraint in your equation and reduce the number of variables thereby to its bare minimum number, which is 1 here instead of 2 in the Cartesian framework, life would become a lot simpler and you'll immediately land up with this equation, which you can, at least in a computer, if you try to numerically solve this, you'll be able to do this given an initial condition like theta 0 and theta dot 0. If that's given to you, you can propagate the solution forward in a computer, whereas this, the immediate question will be, what about lambda t? So you'll actually have to work on this still, and I leave that to you as an exercise to check, that you'll have to work on this to eliminate the lambda t. But how do you do that? Well, to do that you have to again go back to this constraint and say that let us substitute qx is equal to L sin theta and qy is equal to L cos theta, okay, and then take the time derivative of this once, take the time derivative of this twice, plug it in here. So this is an exercise, I urge you to complete this exercise, okay, who knows, it might help you in your exams, yeah. So I urge you to complete this, take 2 derivatives. So first derivative, L, treat that as a constant of course, so you will have qx dot is equal to L cos theta theta dot. Second time you take the differentiation, it will be L cos theta theta double dot minus L sin theta theta dot squared. Keep that on one side. Do the same thing with this fellow, qy dot is equal to L cos theta, sorry, L minus L sin theta theta dot. Second time you do that, minus L sin theta theta double dot minus L cos theta, theta dot squared. So you have Qx dot and Qy dot in terms of thetas. Put it back here. From the first equation, substitute, because 2 lambda appears in common here. Instead of lambda, you can just take 2 lambda. So 2 lambda is equal to mqx dot by qx. Qx is L sine theta. So the first equation, from the first equation you get 2 lambda. Put that 2 lambda in terms of, so you have eliminated qx and qx dot and qx double dot and so on, and gotten everything down to this. Substitute that 2 lambda in the second equation, and knowing what qy double dot is from this equation, yeah, and you should arrive at this exact same equation. The point is not that you will arrive at the same equation, of course you will. The point is that life is a lot simpler, it's just 2 lines here. Whereas in this, you're going about it in a very formal manner. You're not taking advantage of the fact that there is a holonomic constraint here, which should technically make life simpler if you're clever enough to manipulate them and incorporate the constraint already within your framework. That's what physicists would recommend doing anyway, right? When there is a physical constraint, just go ahead and put it in. I'll give you another example, again something I'll not solve but urge you to solve without use of free body diagram. Something that I think almost every one of you has at least encountered during your +2 level courses. So here is, those classic painful examples, right? Pulleys. So you have a mass m1 here, it's an inextensible string, right? So that's crucial. Inextensible means when you solve this, you say this is T and this is also T. If it is not inextensible, then there's 2 different tensions on 2 sides of the pulley, but this is T. So this is how you've been taught. Draw the free body diagram for this and solve for this, because there's same tension on either side, you have to solve for it. And if you remember, it's some difference by sum or sum by difference, some such cool little so-called trick that gave you the acceleration. So whatever the acceleration of this body is, the acceleration of the other body is exactly the same, except that it's going to be in opposite directions. So one is rising, the other is falling, but the acceleration is going to be the same because the tension is the same on either side of the string. And using all those things, you kind of solve for this pulley. But let's look at how our formulation that we've just proposed here works. So suppose this is L1 and this is L2. So what is the constraint here? It's an inextensible string. So the constraint is once again holonomic, you see. This is a constant. The moment you have this, it's very easy to see that L1 dot plus L2 dot is equal to 0, and similarly L1 double dot plus L2 double dot is equal to 0. This is some work that you can already do before even touching this problem from the basic constraint itself. Okay, so I'm not going to use that lambda is what I'm saying, and I'm still going to be able to recover the exact same equation that you are familiar with. How so? So what is the potential energy of this? If you take now this as your datum, earlier in the pendulum we had taken the lowest point as the datum, but again the point of datum doesn't really matter. As I said, it's independent of the frame of reference. Addition of a constant term doesn't really change things. So you have the kinetic energy of this, what is that? m1. L1 dot is its velocity, isn't it? Yeah, this one's velocity is L2 dot. There's only things happening in the vertical direction. Nothing happens in the horizontal direction. There's no wind or anything. So what's the kinetic energy? Half m1 L1 dot squared plus half m2 L2 dot squared. So this is your Lagrangian minus, what's the potential? Minus mg m1 g L1 minus m2 g L2. That's the total potential energy. If this is your datum, this is the length L1, so the potential energy of the first mass is minus m1 L1 g. This is minus m2 L2 g. So when you take a minus sign, it flips sign, so you get plus m1 L1 g plus m2 L2 g. You should be able to solve it now. How? How? Make use of these things. Get rid of one of those things. Why unnecessarily carry the burden of both L1 and L2, L1 dot and L2 dot, if you already know the relations that exist between them, right? Yeah. So this becomes M1 L1 dot squared plus half M2. What is L2 dot? Minus L1 dot. So when you square them, it's the same. L1 dot squared plus M1 L1G plus M2G times, what is L2? L minus L1. L minus L1. Yes? Now we are down to one variable. The variable being L1 itself only, nothing else. Should I complete this or should you be able to do this? Of course, the Euler-Lagrange condition would dictate that L1 is equal to ddt of L1 dot. Is it done? Yeah. So whatever is L1 double dot, the negative of that will be L2 double dot because of this constraint. See, nowhere did we add that constraint. So that's the beauty of the thing. If you have holonomic constraint, you should always attempt to look at it and see if you can get rid of the need for the Lagrange multiplier, okay, and try to put it back in the problem itself by eliminating certain redundant or extra variables. Yeah, and life will be simpler. It's exactly the action, principle of least action at work, right? Any questions up until this point? Yeah, it's fine, right? You see that some difference thing will also come in here, right? This is M1 plus M2, and you know there is a L1 and M1 minus M2 here with L1. So that some difference thing which popped up in your calculations when you did those free body diagrams and all will show up here as well. Just complete this, okay? That's another exercise. Apply this and you will be able to arrive at the Pulley equation. Yes? Yeah. Yeah, that is because of this. L1 plus L2 is equal to L. If you differentiate both sides with respect to time, then L being a constant, the derivative on the right hand side vanishes. So L1 dot is equal to minus L2 dot. It's a speed, right? So L1 dot squared is equal to minus L2 dot whole squared. The minus sign gets off. So L1 dot squared is equal to L2 dot squared. Because energy is not a vector, right? The velocity is a vector, but when you take v squared, that becomes a scalar. It's an energy, right? So that's why the sign is a material here, because it's squared here. So there's no minus sign here. Is that clear? Okay. All right. So enough said about this. I think now you should be able to practice a few more problems as another exercise that I might leave for you, in case you are not convinced that this is a powerful tool. Because of course a single pendulum is okay. We know several different ways of arriving at that equation, but I urge you to try and check this. A double pendulum now. So this is of length L1, this is of length L2, this is a bob of mass M1, this is a bob of mass M2, and this is theta 1, this is theta 2, okay. Try to do this using the free body diagram and then come back to me and tell me how easy you found that to be. On the other hand, use the Lagrangian formalism that we've shown here, yes, and try to find out the total potential energy and the kinetic energy in the system and the difference thereof, which is then going to be integrated to lead to the action integral, and minimize that, and that will help you arrive at the dynamics of theta 1 and theta 2. You see, the constraints are going to be this length and this length, but when you write in terms of the polar coordinates, they're already accounted for. You don't have to worry about adding some lambda times some constraints. Again, because this is a holonomic constraint, right? So try this. This is also another exercise I would again urge you to complete. Okay, attempt to derive the equations of this using the Lagrangian formalism.